This is sections 3.8 and 3.10 of Honors Algebra 2, Functions and Relations. Since a function is a relation, let's start by defining a relation. A relation is a set of ordered pairs. In other words, it's a correspondence between two different sets, your set D and your set R. We call them D and R because they're going to be the domain and the range. But it's a correspondence between two sets. That means a pairing between elements of one set and elements of another, an ordered pair. We can write a relation with a mapping diagram, which is what this first thing is. This is a mapping diagram telling us how we are mapping the items in D to R. So 1 is mapped to both 0 and 2, 2 is mapped to both 1 and 3 is mapped to both 2 and 4. Or we can write a relation in the form of a table, where we have the items in the first column are set D, and the items in our second column are set R. So in this case, this is the same relation as in the mapping diagram. 1 is mapped to both 0 and 2, just as it was in the mapping diagram. Or we can represent it through a graph, where every point on the graph is the ordered pair that pairs something in D with something in R. So 1 in D is mapped to 0 and 2 in R, because we have those 2 points on our graph. The set of first coordinates in the ordered pairs, usually denoted by X, is called the domain. The set of things in D that are mapped to something is the domain. The set of second coordinates in the ordered pairs, usually denoted by Y, is called the range. Those are the things in the set R that have something mapped to them. A function is a special kind of relation. A function is a relation in which each element of D corresponds with exactly one element of R. The words exactly one here are important. It means there is one, so every element of D goes to something in R, and there is not more than one. There is exactly one for every element of D. The domain is the set D. The domain is everything in D, everything that is mapped to something in R. The range is everything in R that gets something mapped to it. In a function, we would say each X gets paired with exactly one Y. X are the items in the domain, Y are the items in the range. So everything in the domain gets paired with exactly one thing in the range. So let's take a look at some examples. Is each relation a function? State the domain and the range. Whether it's a function or not, we can state the domain and the range. So number 1, is that a function? We've got the points 1, 2, 2, 2, 3, 1, and 4, 1. So to check and see if it's a function, we check every element of the domain and see that it has exactly one element of the range paired with it. So the items in our domain, we'll go ahead and state those. The domain is the set 1, 2, 3, and 4. Those are the first elements of every ordered pair there. So those are our values of X. Is each element in the domain mapped to something in the range? Well, yes, they're each part of an ordered pair, so they have a Y value that goes with it. Is there any element of the domain that has more than one thing mapped to it in the range? No. 1 only goes to 2, 2 only goes to 2, 3 only goes to 1, 4 only goes to 1. Is it a problem that there are things in the range that have more than one element of the domain mapped to it? How 2 gets mapped to by 1 and 2, or 1 gets mapped to by 3 and 4. Is that a problem in a function? No, that's perfectly fine. We just can't have an X value that goes to 2 different Y values, but we can have a Y value that has 2 different X values going to it. So our domain is the set 1, 2, 3, and 4. And our range is the set 1 and 2. If something occurs more than once in the range, we don't need to state it more than once. So it's just the numbers 1 and 2. Those are the only things that are mapped to, the only things that have elements of the domain mapped to them. Number 2, we've got the points 1, 1, 2, 1, 2, 1/2, 3, 1/3, and 4, 1/4. Is that a function? Well, let's take a look at the domain. Our domain is the set 1, 2, 3, and 4. Is there something paired with every element of the domain? Yes. Is there only one thing paired with every element of the domain? No. The problem 2. 2 has two things in the range paired with it, both 1 and 1/2. So that's a problem. This means this is not a function. Number 1 was a function. Number 2 is not a function, because 2 is in our domain and it's mapped to two different things in the range. But we can still state the range. The range is 1, 1/2, 1/3, 1/4. Number 3, a mapping diagram. Is that a function? So we take our domain. Our domain here is just the set 1 and 2. Is every element in the domain paired with something in the range? Yes. There's an arrow that goes from 1. There's an arrow that goes from 2. Is everything in the domain paired with only one thing in the range? No. Problem is with 1 that goes to both 3 and 4. Everything in the domain can only go to one thing in the range. So that's a problem. This is not a function. So it is a relation still, but it's not a function. And the relation has a range of 3 and 4. Okay, number 4, I've just given you a line, that green line there. And that is a function because every element in the domain here being the x-axis, if I pick an element in the domain, like that one right there, there is exactly one element in the range that goes with it. It's that point there that corresponds to this y value over here. Every element in the domain has exactly one element of the range. No matter which number I pick for x, there's exactly one value that goes with it. So yes, this is a function. Now to tell whether or not a graph represents a function, we have something called the vertical line test. What that says is, if I take any vertical line and I pass it through my graph, if that vertical line ever crosses my graph more than once, it's not a function. If there's any place I can put my vertical line where it crosses my graph more than once, then my graph is not a function. If everywhere where I can put the vertical line it only crosses my graph exactly once, then it is a function. So for example, in this first one here, my graph is that purple line, or that purple curve. And if I pass a vertical line anywhere here, say that one, all I need is one of them, and it crosses my graph twice. Once on the top part, once on the bottom part. So that's a problem. It does not pass the vertical line test because I found a place where I can put a vertical line where it crosses my graph more than once. That means this is not a function. How about the second one here, a circle? Well, I can put my vertical line, say, there. It crosses my graph twice, so it's not a function. How about the third one here? Well, if I put my vertical line, say, there, it only crosses my graph once. If I put it there, it still only crosses once. If I put it there, it only crosses once. If I put it there, it only crosses once. If I put it there, it only crosses once. So this does pass the vertical line test. Everywhere that I can put a vertical line, it only crosses my graph exactly once. There's never any place where it's going to cross more than once. So this is a function. And how about the fourth one, a parabola? We can check, and everywhere where I can put a vertical line, it's only going to cross once. So it is a function. So we can define functions through a graph, through an equation, through a mapping diagram, through a table, or through a rule. Example of a rule, we can define the function f such that for any x in the integers, so the integers are my domain, we're going to define this function to take every x in the integers to the value 2x. We're going to double x. We're going to double everything in the domain. The domain of the integers, positive and negative whole numbers, and 0. What would be the range then? Well, if I take a positive number and I double it, like 2, I'm going to get 4. If I take 3, I'm going to get 6. If I take 4, I'm going to get 8. We can only get then even numbers. 0 will map to 0, and 0 is an even number. Negative numbers will only map to negative even numbers. Negative 2 will map to negative 4, negative 3 will map to negative 6, negative 4 will map to negative 8, and so on. So the range will be all even integers. Another way we can write the same function instead of in words is to use what's called arrow notation, where we say f is the function such that x goes to 2x. So that f and the colon are just notation saying the function such that x is mapped to 2x. The arrow means it's mapped to, it goes to. So the value x goes to 2x. Or we can use function notation, which says we have the function f with the variable x. It takes x to 2x. It takes what's inside the parentheses and it does to it what's on the other side of the equal sign. You'll see that notation throughout this course and in later courses. So for example, for each domain D, so here's 3 different domains, state the range of the function f, which takes x to the absolute value of x plus 3. So number 5, I've only got 5 elements in my domain, negative 2, negative 1, 0, 1, and 2. So my range is going to consist of the 5 things that are mapped to by those 5 elements of the domain. So if I take negative 2 into my domain, or into my function, I'm going to find f of negative 2 then, and f of negative 2 is going to be what I get when I substitute negative 2 in for x. I'm going to have the absolute value of negative 2 plus 3, which is the absolute value of 1, which is 1. So 1 is in my range. And I can take negative 1 and find f of negative 1, and f of negative 1 with the absolute value of negative 1 plus 3, which is the absolute value of 2, which is 2. So 2 is in my range. If I take 0 and I plug it in for x, I'll have the absolute value of 0 plus 3, which is 3, or the absolute value of 3, which is 3. So f of 0 is 3. If I plug in 1, I'll have the absolute value of 1 plus 3, which is the absolute value of 4, which is 4. And if I plug in 2, I'll have the absolute value of 2 plus 3, which is the absolute value of 5, which is 5. So I got my elements of the range by plugging in my elements of the domain and finding the value of the function. So there's my range, 1, 2, 3, 4, and 5. Number 6, what if my domain was any x such that x is greater than 3? So not just whole numbers, not just 4, 5, 6, and 7, and so on, but also all integers and decimals bigger than 3. Well, what would happen at 3? I would get 6, right? If I take something bigger than 3, I'm going to be adding 3 to it and then taking the absolute value. Well, it's going to be bigger than 6 then. And in fact, I could get anything bigger than 6. If I want to get 6.1, all I have to do is plug in 3.1. I'll have the absolute value of 6.1, which is 6.1. So I can take anything bigger than 6. So my range then, I could express it as the set of all y, such that y is greater than 6. Notice we're using the colon here to mean such that. Before we used the vertical line to mean such that. Either one is acceptable. They're both used universally by mathematicians. And number 7, what if the domain is the entire set of real numbers? If I take any real number and I plug it in for x, what am I going to get? Well, I've already seen that if I take a number bigger than 3, I'm going to get a number bigger than 6. But if I take a number less than 3, if I take 2, what am I going to get? I'll get 5. What if I take negative 2? Well, we already saw number 5 that we'll get 1. What if I take negative 6? Well, negative 6 plus 3, which is negative 3. The absolute value of negative 3 is positive 3. Okay? What if I take negative 4? Well, negative 4 plus 3, which is negative 1. The absolute value of negative 1 is 1. What if I take negative 3? Well, negative 3 plus 3, which is 0, and the absolute value of 0 is 0. Can I get anything less than 0? No, because absolute value will always be positive. So it turns out my range is all positive real numbers. A simpler way to write that is to use the symbol for real numbers and then put a plus sign as sort of an exponent, but it's just notation. For R plus, all positive real numbers. And 0. Because 0 is not considered a positive number or a negative number. So anytime 0 is included, we need to state that. We could say all non-negative real numbers, and that would be all positive numbers and 0. But we need to be careful with 0. Now what if f of x is 2x minus 1? So that's my function f. It's going to take x to 2x minus 1. And my function g takes x to x squared plus 1. So two different functions, f and g. Let's find these different values. Let's find f of 2. So f of 2 means I plug in 2 for x in my function f. That's going to be 2 times 2 minus 1, which is 4 minus 1, which is 3. So f of 2 equals 3. I just plug in 2 for x and evaluate it. Okay, f is not a variable. F is just notation indicating a function. Same with g here. So g of 2 is going to be 2 squared plus 1. 2 squared is 4, plus 1 is 5. So g of 2 equals 5. Now, part C asks for f parentheses, g parentheses, 2 parentheses, parentheses. We read that as f of g of 2. And we always start on the inside. It's like a machine where it's taking 2 as its input, performing g to it, and whatever it gets out from that, it's taking into f and performing f onto it. So first we do g of 2, and we already know g of 2 equals 5. So the way this works is it takes that value that we get out of g and it plugs it into f. So that means we need to take f of 5. That's what came out of g. That's what came out of the inside function. So that number went inside there. F of 5 was 2 times 5 minus 1, which is 10 minus 1, which is 9. So f of g of 2 equals 9. We do the inside function first, take what comes out of that, the answer for that, and plug it into the outside function. So like in part D, we're doing the opposite. We're doing g of f of 2. We already know f of 2 equals 3. That's what we got in part A. Now we're going to take 3 and we're going to plug it into g. We're going to do g of 3. So g of 3 is 3 squared plus 1, which is 9 plus 1, which is 10. So g of f of 2 equals 10. If a function does not have a specified domain, so if we're not told what the domain is, its domain is a set of all those real numbers for which the equation produces real numbers. So everything that we can plug in and get something out of, then everything that we can plug in is in our domain. So for example, find the domain of each function. So part A, f of x equals 1 over x minus 2. What we're looking for are numbers that we could plug in for x that will not give us a value out for f. What we need to be careful of here when we have a fraction and the variable in the bottom of the fraction is when the fraction has a denominator of 0, because we cannot do 1 over 0. Remember, 1 over 0 is undefined. So that's what we need to be careful of. So we need to take our denominator, x minus 2, set that equal to 0, and find the value of x that makes that 0. It's pretty easy to find. It's just 2. So 2 cannot be in our domain. So the domain then is all real numbers except 2. Part B, g of x equals 1 over x times x plus 3. Again, we're looking for things that make the denominator equal to 0. So if my denominator equals 0, that means either x equals 0 or x plus 3 equals 0. Because when two things are multiplied together to be 0, one of them has to be 0. So that means x cannot be 0, and x cannot be negative 3. So what we need to do is throw those two things out of our domain. So the domain is all real numbers except (0) and negative 3. Another way that we can write that is to say we'll take x less than 0 or x between 0 and, we'll take x less than negative 3 x less than negative 3 or x between negative 3 and 0 or x greater than 0. That's another way we could write that domain. Anything less than negative 3, anything bigger than 0, anything between negative 3 and 0. Part C, h of x equals the square root of 2 minus x. So this time we don't have a fraction, so we don't have to worry about the denominator of a fraction being 0. But what we do have to worry about whenever we have square roots is that we cannot take the square root of a negative number. The square root of, say, negative 4 does not exist. The square root of any negative number is not a real number. So what we need to be careful of here is anything for which 2 minus x would be less than 0. If it's less than 0, we cannot take the square root of it. So we need 2 minus x to not be less than 0. That means we need negative x to not be less than negative 2, which means we need x to not be greater than 2. I divided by a negative 1, so I switched the sign. So I do not want this to happen. I can't have x be greater than 2. So what is my domain? My domain is everything, the set of all x, such that x is less than or equal to 2. And then it will not be greater than 2 and will not cause a problem. We'll look at a lot more examples of that in class. Here are your immediate practice problems. Let f of x equal 4x minus 10 and g of x equals x squared minus 2. Find f of 5, that means you're just plugging in 5 for x into f and evaluating it. Find g of 3, so you're plugging in 3 for x into g. And find f of g of 3. That means you're plugging in 3 into g first, so take your answer from number 2, and then plug that answer into f, and that will be f of g of 3. And that is the end of sections 3.8 and 3.10.